This is a short revision video on electromagnetic radiation equations for advanced higher chemistry, and this is the inorganic section. So electromagnetic radiation is something that is used frequently in chemistry, but it's not something that's been discussed in a lot of detail in previous years. Visible light is just part of a wider spectrum of radiation, and we've got 7 components, all of which can be involved in different aspects of chemistry. So we have radio waves, microwaves, infrared radiation, visible light, ultraviolet light, X-rays and gamma rays. Now those are organised from those containing the lowest energy on the left hand side to the highest amount of energy on the right hand side. They're also organised in terms of wavelength, how long the wave is. So radio waves are the longest and gamma rays are the shortest. You need to know the 7 types of electromagnetic radiation because you can often be asked a question identifying the odd one out, which one is not a type of radiation or which one is from a list. And you're occasionally asked to be able to sequence them in order, but only in a multiple choice fashion. Identify which sequence shows them going from longest wavelength to shortest wavelength, or lowest energy to highest energy, etc. Now, the wavelength is what makes these waves have different energies. And the wavelength, the symbol is like an upside down Y, and it is called lambda, lambda for length. It is typically given in nanometers or in meters. And the conversion is that 1 nanometer is equivalent to 1,000 million or a billion. 1 meter is 1,000 million nanometers. 10 to the minus 9 is your conversion for turning nanometers into meters. Now, when it comes to electromagnetic radiation, all electromagnetic radiation travels at the same speed. This speed is the speed of light, which is in your data booklet on the last page, and it is 3.00 times 10 to the 8 meters per second. Now, if you do physics, this number might be slightly different in physics, but in chemistry, make sure you're always using 3 times 10 to the 8. Wavelength and speed are related to one another by this equation, where speed is equal to f lambda, where f is the frequency. And frequency is essentially the number of waves that pass through a point per second. Now, the units of frequency in physics will be hertz, but in chemistry you will often see it by just seconds to the minus 1. You are allowed to use either unit, but if you're not doing physics, it might be helpful in terms of keeping the units straight in your head to just use seconds to the minus 1. And each type of electromagnetic radiation, because it has a unique wavelength, will also have a unique frequency. Now, in a confusing fashion, we've got a terminology to describe electromagnetic radiation as wave-particle duality. This means that even though we are used to light being a wave, we can also imagine it as a particle. How I view this, the analogy I use, is that if electromagnetic radiation is like a bullet being fired from a gun, the wave is the route that it took, and the bullet is the particle that has the energy and is traveling. The pathway is the wave, the bullet is the particle. It has both qualities. Now, what we call a particle of light is a photon. So when a photon is emitted or absorbed by anything, it will either lose energy if the photon has been emitted, because that photon contains energy. And if you absorb a photon, you're going to gain the energy that the photon had. And we can use an equation, two different equations for working out the energy. We can use the energy is equal to this value h multiplied by the frequency, or because frequency is related to the speed of light and the wavelength, we can use instead energy is equal to h speed of light divided by the wavelength. You'll choose the equation based on whether or not you were given the wavelength or the frequency. And the value h is known as the Planck constant. It is a very small number, 6.63 times 10 to the minus 34, and it is again in the back page of your data booklet. And importantly, your wavelength must be in meters. So if you're given it in nanometers, you must do a conversion. So when it comes to wavelength units, we've just said that the wavelength must be in meters. But in chemistry, because we like all of our numbers to fit between 1,000 and 100, we usually use nanometers. And so you need to be able to do a conversion. If you want to turn your nanometers into meters, you just multiply whatever number it is by 10 to the minus 9. By 10 to the minus 9. Doesn't matter if you say it doesn't go, if you think it goes against scientific notation, having something like 200 times 10 to the minus 9, it's absolutely fine. It's just for use in your calculator. So for example, 250 nanometers is 250 times 10 to the minus 9 meters, and that's what you would use in your calculation. But always be careful, because maybe they will give you the value in meters to start with. So only do this if you've been given nanometers. If you want to turn meters into nanometers, you multiply by 10 to the 9. It's really important that you check whatever units the question is after and to do the correct conversion. And if no units are specified, you're allowed to use either meters or nanometers, but you must include the unit that you've chosen so that you can get a mark for units. Another confusing thing that can sometimes happen is that instead of a wavelength, they may give you a wave number. And this is especially true for infrared spectroscopy, something you will learn about in Unit 2 and Unit 3. Now the wave number is lambda to the minus 1, or just 1 divided by lambda. And remember, lambda is our wavelength. It is typically given in centimeters to the minus 1, which is a very annoying unit. So if you divide the number 1 by your wave number, you will get a wavelength in centimeters. So to turn wave number into wavelength, just divide 1 by the wave number. Now that will give you an answer in centimeters. To turn centimeters into meters, you then divide by 100, and then you can do your equation using meters. Now, another important aspect of this is that if you use those equations, E equals HF or E equals E equals HF or E equals C over lambda, you get energy in joules. Now, the joules associated with a photon is very, very, very small. In chemistry, we don't like joules because it's tiny. We like numbers that fit between 100 and 1,000. So we usually use kilojoules per mole. So we need to modify our energy equations in order to get our units. So what we add in is this new letter, this capital L in each equation. Now L is what is known as Avogadro's number. And Avogadro's number is basically the number of particles, or the number of atoms, or the number of molecules that make up 1 mole. A mole is just a quantity of things. In the way we would say a grand means 1,000, a mole means 6.02 times 10 to the 23. And that again is found alongside the Planck constant and the speed of light in your data booklet on the back page. Now, when we use these equations, annoyingly, it still only gives us values in joules. That L is what gives us our value per mole, but we don't yet have kilojoules, we only have joules. So if we want to do the conversion into kilojoules, we must divide by 1,000. Now that step and the dividing by 1,000 is not in your data booklet. You need to remember that the energy equations only ever give you values in joules. So if you want kilojoules, you need to divide by 1,000. The final thing is just to let you know in which scenarios you could be asked to use these equations. So the main one would be you're given a wavelength and you're having to calculate given a wavelength or a frequency, and you have to calculate the energy of a photon, in which case you'll use the equations without L, or for a mole of photons, in which case you'll use the equations with L, Avogadro's number, included. You might be told that the energy of a bond has a particular value in kilojoules per mole, and then be asked to calculate the wavelength. So what you would do is rearrange the equation to make a wavelength as a subject. Similarly, you could be asked to work out the wavelength of light needed for an ionization energy, and you'd need to be given that ionization energy in kilojoules per mole. Or you could be asked to work out the energy of a value from a wave number. So you would need to convert the wave number into a wavelength and then work out the energy.